Have you ever really looked at the world around you and wondered about the invisible rules that make it all work? You know, the little things like why rain forms perfect little drops or how a paper towel can magically soak up a huge mess. Well, we're going to dive into that today. We're exploring two of nature's tiniest, but honestly most incredible superpowers, surface tension and capillarity.
It all starts with a question. Just look at this little guy, a water strider. He's not swimming, he's literally standing on the water. Now, he's heavier than water, so he should sink, right? So how in the world is this possible? What is holding him up?
The answer to that question lies in something you can think of as an invisible skin that forms on the water's surface. And right now, we're going to pull back the curtain on this amazing force of nature.
Okay, so the hero of our story is this thing called surface tension. Basically, it's this natural urge for a liquid surface to shrink and pull itself tight, almost like a stretched out rubber sheet or a balloon. It's the reason why liquids are always trying to get into the smallest, tightest shape they possibly can.
And this quote right here is probably the best way to picture it. Just imagine that every drop of water, every puddle, every lake is covered by this super thin, flexible, invisible skin. And that skin is at the heart of everything we're about to see.
So where does this skin even come from? Well, it's not magic, it's pure physics. It all comes down to a constant battle happening at the molecular level between two key forces, cohesion and adhesion.
All right, let's break this down. It's simple. Cohesion is the force that makes molecules of the same stuff stick together. Think of it like teamwork. All the water molecules want to hold hands with other water molecules. Adhesion, on the other hand, is the attraction between molecules of different things, like water wanting to stick to the side of a glass. And whoever wins this molecular tug-of-war totally dictates how a liquid is going to behave.
And this right here shows you exactly why it happens. See, a water molecule deep inside the liquid is getting pulled on equally from all directions by its neighbors. It's totally balanced. But a molecule right at the surface, it's got no water molecules above it, so it gets pulled down and sideways by all its buddies below. And it's that constant inward pull that creates the tight, elastic membrane we call surface tension.
Now, you might hear people use the term surface energy sometimes, and it can get a little confusing. Here's the deal. For what we're talking about today with liquids, they are basically the same thing. Think of them as two sides of the same coin. Tension is the force, energy is the energy it takes to make that surface. Worth is going to stick with tension to keep things simple.
Okay, so now we know about the forces that are at play. Let's take a look at the really cool part. The beautiful and sometimes kind of weird ways they actually shape the liquid world that we see every single day.
This is a perfect example of cohesion just totally winning the fight. The water molecules here are way more attracted to each other than they are to this waxy surface. So, to get away from the wax and hang out with each other as much as possible, they pull themselves into the one shape that has the smallest possible surface area, a sphere. It's exactly why rain beads up on a freshly waxed car.
This same battle explains the meniscus, you know, that little curve you see when you look at a liquid in a glass tube? With water and glass, adhesion wins. The water molecules get pulled toward the glass, so they start climbing up the sides, and that makes this concave U-shape. But mercury, it's the total opposite. Its cohesive forces are incredibly strong, way stronger than its attraction to glass, so it pulls away from the walls, puffing up into a little convex dome.
So we've seen how these forces create tension and shape. But what happens when they work together in just the right way? Well, that's when we get our second superpower, this mind-bending, gravity-defying climb called capillarity.
So let's ask the question. We saw water climbing up the walls of a glass because adhesion was winning. What do you think happens if we make that space really, really narrow?
What happens is capillary action. You might also hear it called capillarity or wicking, and it is the incredible ability of a liquid to flow upwards, seemingly defying gravity itself, all because of that teamwork between cohesion and adhesion inside a tiny little space.
This shows you exactly how it works. First, adhesion, the stickiness to other things, makes the liquid climb the walls of the narrow space. But then, cohesion, that water-sticking-to-water teamwork, kicks in and pulls the rest of the liquid right up along with it. It's this continuous cycle of climbing and pulling that just marches the entire column of water upwards straight against gravity.
And you know, there's even a rule for this. It's called Jurin's law, and it's really simple. The thinner the tube, the higher the liquid climbs. That's it. A narrower space gives adhesion more power to pull the liquid up. So, up it goes.
Okay, so we've got the science down. But so what?
why does any of this matter? Well, let's put it all together and see how these tiny little superpowers are absolutely everywhere, shaping life and technology in ways you probably never even thought about.
I mean, really think about it. How does water get to the top of a giant redwood tree? That's capillary action in its tiny little tubes. A paper towel soaking up a spill? That's a whole web of tiny fibers creating spaces for water to just climb right in. Those fancy gym clothes that wick sweat away? Same exact principle. It's everywhere. From the tears of wine on a glass to how ink flows in a fountain pen, it's all powered by these same two forces.
And the reason we see all these things so dramatically with water comes down to this number right here. Water has an exceptionally high surface tension, one of the highest around, and it's all because of the strong bonds between its molecules. That high cohesion is what gives water its super strong skin and its amazing climbing skills. So, when you get down to it, these tiny little forces, born from the simple attraction between molecules, are powerful enough to let an insect walk on water and to keep the tallest trees on Earth alive. It really makes you stop and wonder, doesn't it? What other invisible forces are out there, quietly shaping our world in ways we can't even see?